We are Group 1 and we built an inverted pendulum. The goals and milestones we had for this project were straightforward. The first was to actually build the inverted pendulum on a car with free wheels that are driven by a motor. The second goal was to design and analyze the controller and process for a stable inverted pendulum. This involves starting with finding the equations of motion, then finding the open loop transfer function, and then finally a closed loop transfer function. The third goal is to install an accelerometer and gyrometer on the pendulum axle to measure the angle of orientation of the pendulum itself. The final goal is to use the angle reading and the closed loop analysis to implement a stable feedback loop to control the inverted pendulum angle. To build the pendulum, we started with an RC car from Walmart and stripped it down to the axles. We then cut some lightweight shelving wood to the width of the axles and mounted the axles to the wood using pipe strapping. The final step was to mount the steel rod we used as a pendulum on some bearings inside wood posts. To control the motors, we used an Arduino Mega that one of us already owned and an Adafruit motor shield. The reason we went this route for motor control is because it allowed us to easily translate the sensor feedback into a variable motor speed in the code without any extra circuitry.
For the accelerometer and geometer readings, we chose the MPU 6050, which is an accelerometer and geometer combination. This gave us all the readings we needed in one chip. We mounted it on the end of the axle of the pendulum. The first thing we did in creating the code for the sensor readings was to create a transfer function for the accelerometer so that the two significant axes were producing the correct readings at 0 and 90 degrees. Based off the acceleration due to gravity, the next big step was to get the angle from the gyrometer. The gyrometer readings are in degrees per second, so taking the integral of that over a unit of time produces the degree displacement over time. We did that by multiplying the gyrometer readings times the loop time, which is 4 milliseconds. Finally, we combined the two readings using a complementary filter to compensate for the accelerometer's instability and the gyrometer's drift over time. As you can see, the coefficients we found were 0.097 for the gyrometer readings and 0.03 for the accelerometer readings. So as you can see by this graph, the filtered sensor readings are almost perfectly matched with the measured angles.
So to build the open loop transfer function, we started with the block diagram, as you can see in the top right. So for inputs, we have the disturbances in cart acceleration, and then the output is the angle of the pendulum. So then at the bottom, you can see that we linearized our equations of motion and had the same input and output combinations using the approximation that theta is equal to 0. Then we took the Laplace transform and solved for h of s by isolating the inputs and outputs. So now to change the open loop system into a closed loop system, we changed the cart acceleration into a sensor feedback loop of the angle. First, we looked at using purely proportional feedback, but that wasn't going to work. So we used one pole always in the right-hand plane. So we settled on a proportional plus derivative controller, which allowed us to achieve a stable system, moving the right pole into the left-hand pole. So here we can see in calculation, the controller efficiency, we set two goals to achieve for. So the first was an overshoot of 2%, which gives us a zeta of 0.78. And then that let us create an equation for K2 and K1. Our second goal of a 4-second settling time gave us another equation. Then it was just solving for K2 and K1. Ultimately, our poles were at negative 1.02 plus or minus J 0.81, which gives us stability.
And with the sensor readings already taken care of, our next step was to create the PD controller. We did this by calculating the angle deviation from 0 for the proportional term, and for the derivative term, we derived the angle divided the angle deviation by the loop time. Then you can see in the motor speed line, we applied the KD and KP proportional terms to calculate our motor speed. Then we created a motor control function with these three constraints in mind. If the angle is greater than 45 degrees in either direction, we set the motor speed to 0 to prevent the motor from driving after the pendulum falls. And then the other two considerations were the direction that we wanted the motor to turn in, depending on which way the pendulum was falling. So here are 3 videos of our code running. So as everyone saw there, we could not get the system to work. With very minor angles, the system would oscillate around 0 briefly, but would never reach stability. With anything greater than that, we could not accelerate fast enough to correct the pendulum's fall. As the image on the right shows from our serial monitor, even with maximum motor speed at small angles, this was true. So some of the reasons for our lack of acceleration are a lack of traction for the cart and a too high center of gravity, allowing the cart to tilt backwards when it accelerates. In order to fix this, we could add weight to the base of the cart to lower the sense of gravity and add power to the front axle to increase torque, acceleration, and traction. This would also allow us to prevent motor speed saturation too soon and to reduce controller gains, which would allow us to get greater stability in the system. And so all in all, that's our inverted pendulum project.